start the recording here. Okay, so today we just want to continue on with solving the Schrodinger equation in 3 dimensions for radial potentials. We kind of did halfway and stopped in the previous class, so now we are continuing on the rest of the story. Right, here is at the moment we are saying that we are solving the Schrodinger equation where the potential energy function is a function of r only, where r is the distance from the origin, right? But later we will go to the case of solving the case of the hydrogen atom. And as we mentioned last time, right, I'm gonna remind you guys what we have been doing in the previous class, that we are using spherical coordinates. So spherical coordinates means a point, instead of using x, y, z to describe the point, we will be using the angle theta, and then phi, and then r. So still 3 dimensions means we still need 3 numbers to specify a position, but we use a radius and 2 angles, right? So this is our spherical coordinates. Okay, so our Schrodinger equation for radial potential looks like this. We did this last time in the previous class, right? My Schrodinger equation for my position wave function is d psi dt, and then the kinetic energy operator is just the Laplacian, right? And then now I want to consider the potential energy that is a function of r only, doesn't depend on the angles. So I have also shown you last time that we can do the separation of variables of the t. So we separate the t out so that we get the time independent Schrodinger equation is h bar square over 2m, and then the Laplacian of the psi, and then plus the potential energy is equals to E psi. So we are focusing on the case where my function v, to emphasize again, it depends on r only, and it is independent of the angles theta and phi. Okay, so that is what we did last time, and we assume that for the separation of variables, we suppose that my function theta r phi is a multiplication of 3 separate functions, which is the r, the theta, and the phi, right? And from here, we left off at the end of the Monday's class. We stopped at this point, right? So we managed to separate the r equation out. So it is dr, right? So this is a second order ordinary differential equations, right? So mr squared over h bar square v minus e, and then is equals to l plus 1, right? So everybody here contains r only. See, my v depends on r only. So this is the equation purely for r, for the r variable, but the other one is still mixed in terms of angles. The other one still looks like this. So it's 1 over theta d theta, and then sine theta d theta, and then 1 over phi sine square theta, and then second derivative of phi. Okay, so there's a sine here and a sine square here, so be a bit careful, right? So this is a constant, but we purposely write it as the constant in this way. Okay, so the first equation contains r only, but here contains theta and phi. So we still need to further separate this second equation. So let us continue. Okay, let me check again just to make sure. Yeah, let us continue. Okay, so we further separate equation 3. And the way to do this is actually not too bad. It's not too difficult. We just need to multiply both sides by sine theta. So this is the part where it's mixed, you see. This one, theta only, fine. This is a constant, so not a big problem. But this one is a mixture of theta and phi. So if I multiply this equation by sine square, then this part will no longer have theta. Then theta here is still okay. So we're going to do this. We're going to multiply both sides by sine square theta, right? So multiply by sine square, this becomes sine theta over the function, and then d theta, and then sine theta, and then d phi d theta, and then multiplying by sine square is 1 over phi d2 phi d phi square, and then this is negative l plus 1, sine square theta. So I'm going to bring this to the left hand side, so that if I bring this here, this is going to be this, right? Sine theta d phi d theta, and then this one bring over, I got LL plus 1, and then sine square theta, and then this part contains phi only, so phi d phi equals to 0. So now we can separate, because this one contains theta only, this contains phi only. So how can a function of theta plus a function of phi be equals to 0? It just means that the only possibility is these are constant functions. So constant function, and it is some constant k, but since we know the answer, or since I know the answer already, right? You guys are seeing this for the first time, but since the textbook knows the answer already, we know that in the future it is going to be a square root of something. So we write this as we write this constant purposely as a m squared. But this is also another constant, and I want this to be 0. So this constant plus some other constant, to make it 0, it must be negative of the same. Whatever this is, this must be the negative version. Okay, so this gives us a differential equation, right? So this thing is equal to m squared, which is to say that sine theta over this sine theta d phi d theta, and then plus LL plus 1 sine square theta equals to m square, and this gives me 1 over phi d 2 phi d phi square is equals to negative m square, right? So now we have separated 1, 2, and 3 ordinary differential equations. So yeah, so let us collect the equation in one place just to see how it looks like. The first equation was the R equation, dr, right? And then minus 2mr squared over h bar square, potential minus E, and then this equals to LL plus 1. Should I manipulate? No, just keep it like this for a moment. And then this theta, right? Let me multiply the theta up so that we have sine theta d theta, sine theta d phi d theta plus LL plus 1 big theta sine square is equals to m square and the theta function, right? So this is the ordinary equation for a differential equation for theta. And finally, the phi equation is the simplest one to solve. In fact, you can already guess the answer, right? This is just a simple ordinary equation like for the harmonic oscillator. But yeah, so these are the 3 equations that we want to solve. So we're going to spend quite some time solving these 3 equations. And yeah, unfortunately, it's going to be a bit boring, because it's going to be full of math, and we're going to spend some time trying to work out the solutions like this. Okay, any more questions so far? 3 variables, do we assume total function is a multiplication of 3 function? I comes out. Yes. So correct. Yeah, so yeah. Okay, so the first question is yes, because for 3 previously we have we have how many, what did we do last time? T and X, right? Then we assume that. So for any number of variables, for 3 variables, then therefore we separate 3 functions, because the reason is because the partial differential equation is having derivatives of r, having derivatives of theta, having derivatives of phi. So I got 3. So in order to separate them, I need 3 separations. Yeah, so I is going to come out again. Exactly. And correct. Your answer is correct. But for this case, instead of sine and cosine, I will use the exponential. So this is where the I comes in. Okay. So I already say 1, but let me restart the numbering. So this equation 1, equation 2, and equation 3. And like I said, we will spend quite some time to solve these 3 equations, and they are so complicated and going to be a bit messy. So therefore, unfortunately, today's class might be a bit boring. But the first one, yeah, it is the usual harmonic oscillator ordinary differential equation. This one can be solved by power series. This one is, we will also solve this by power series. In fact, I will skip the details for equation 2, otherwise we will spend like 10 hours solving the entire thing. But it's already gonna be complicated enough as it is, so we're gonna mainly solve equation 1 and 3. Okay, now before we start, right, notice we make some observations, so let's make some remarks. The first one is, like I said, right, we haven't said what is the function v yet. So at the moment we haven't said anything about v. So the only assumption that we make here is v shouldn't depend on r, otherwise this is not separated anymore, right? So the only required that v is independent of angles. Okay, so yeah. And like I said, we haven't specified yet, but for later we want to talk about the hydrogen atom, right? So let's do a bit of a preview. We're gonna substitute this but a bit later, but at least you can kind of, I will show you now, so again at least we can imagine what's going on, right? So what does the hydrogen atom consist of? It consists of a positively charged proton, right, of charge positive E, and then there's a negative electron, and then the distance r. So the v here describes the potential energy of this system, and therefore it is negative E squared over 4 pi epsilon r. So this is what we learned in electromagnetism, right? And in fact, this is just one example of a radial potential, but we can talk about other things as well. So for example, let's give another simple example, helium ion. Okay, so helium ion means He positive, right? What is a helium ion? Helium ion is ionized helium. Helium consists of, the nucleus consists of two, well, for this particular isotope you have 2 protons and 2 neutrons. Neutrons have no charge, the proton has positive charge of twice of 2 of this, 2e, right? And then helium ion means 1 electron has been ionized, therefore we got 1 electron here, so that my potential energy is just this q times this q, so it's negative 2e squared over 4 pi epsilon r, right? So this is just e squared, but for helium ion is 2e squared. Okay, and then we can write down potentials of all other kinds of things as well. But in any case, this is just a preview. We will not substitute this quite yet, because we will first talk about the angular equations. So the angle equations, right? The angle equations, look, the potential energy doesn't appear anywhere here. The v depends on r, it comes here. So this one doesn't depend on potential energy, right? So the theta and phi equations do not contain v. So we can actually solve them for any system without actually saying whether this is a hydrogen or a helium or anything. The solutions for the angle functions is going to be the same. The same for any VR. And this is going to be a big deal for later, because these solutions will be called spherical harmonics. So I don't know if you have heard this in other places, but we will at least partially derive some properties related to the spherical harmonics. So spherical harmonics is going to be very important in many different areas of physics. Okay, so any questions so far? Why not summation? What do you mean? Oh, summation. You can try. You can't separate it. If you for certain partial differential equations, you can't use the r plus theta plus phi, right? So you substitute in and see, you can't separate it. Okay, but for Schrodinger equation we can't. But in theoretical mechanics, there are separation of variables using summation. It's called the Hamilton-Jacobi equation. but but that is for mechanics, so we won't be using this here. Okay, but the simple answer is, yeah, if you try summation, you can't really separate them. Okay. So if there's no it's too dark. If there's no other question, let us start solving the angular equation. So let's start with the phi equation. So let's try to solve equation 3. This is the next topic, 5.3.2, solving the angular equation. Okay, so firstly let's start with the phi equation, which is very simple, right? And yeah, you guys already know, you have already mentioned the solution already. And yes, to answer the other question again, m squared is just another constant, right? The main point is m squared, square of a constant is another constant, but the reason why we purposely write it m squared is because later we'll realize very soon it's going to be an integer. So it's going to be some integer square over here. And yeah, so we got the solution over here, which is just ae I m phi, right? And then another solution is be minus im phi. But this is one solution, this is another solution. We can also just write one term is enough. And where m is positive or negative. Okay, so this one is like, this is two linearly independent solutions. And another way to look at it is this is like a superposition. So this superposition of function with m and then plus another solution with a negative m. So we just need to write this once is enough, and then this is like a superposition of one solution with a positive constant and another solution with a negative constant. Okay, so where m is positive or negative. So at the moment, m is a constant, right? We don't know what this is yet. But I will show you that this is going to be an integer. Why? Well, let's see. This is page 3. The main reason is because phi is an angle. So since phi is an angle, then if it's an angle, you know, this and phi plus 2 pi actually is the same point, right? So refers to the same point. Okay, so that means this function, right, whatever function this is, if you increase by 2 pi, by right we should come back to the original position. So it should give us the same value as this, otherwise it's like nonsense, right? How can a function be equal to two different things? Cannot be, right? So yeah, it's the same point, so you should come back to the same thing. But we look at this equation. Okay, so we look at this equation is aeim phi plus 2 pi, so it's 2 pi I m, right? And then this is equal to aeim phi. So the aeim phi will cancel each other, so what we left with is just the a also cancels, so the e 2 pi im is equals to 1, right? So this is I is a complex number, and how do I make sure that this is equals to 1? Remember that this, if you use the Euler formula, right, this is cos 2 pi m plus I sine 2 pi m. So the only way to make sure that this is equals to 1 is that m is an integer. Okay, so this is the reason why m is an integer, right? So m itself. So now we know why we purposely write this as a square root of m. And then just now the ll plus 1 also is going to be the same story. Okay, so yeah, we have solved the phi equation already. So in summary, it's basically just aeim phi, where m are integers. Okay, so this is the symbol for integers. Yeah, so we solved equation 3. What's next? Well, next one is the theta equation. Okay, so theta equation is let me write this here, d theta, sine theta, d phi d theta, right, plus L plus 1. See, this is a constant, but we purposely write L plus 1 because later we realize that there has to be a integer as well. For a similar reason, but in a more complicated way. Okay, and our equation for this. So now we know this m is the integer over here. How to solve this equation? Well, it's a bit messy, so I will not show you how to solve it. I will just give you the answer. Okay, so good, right? You this is what you want, I hope. This is good news for you guys. Okay, so the solution is given by the theta, right? I will not show you how to solve it, but they are solved by special functions. Okay, so this is a special function called, I haven't told you what this is yet, right? This is almost feels like I'm just renaming things, but this is a special function called the associated Legendre function. Okay, and what does this mean? Well, to express our associated Legendre function, we let x equals to cosine theta, and I can express everything in terms of x now. Okay, so this x is, the formula is given by 1 minus x squared, and then I take the modulus m over 2. So m is an integer, we could be positive or negative, but let's make it positive and then half. Right, so it's the square root of this function to the power m. And then I differentiate m times. Okay, and what am I differentiating? I'm differentiating PL. Now, okay, what is this now? Right, this is another function where this is called the nth Legendre polynomial. So the nth Legendre polynomial is given by PLX is 1 over 2 to the power L factorial, and then I differentiate this L times. Okay, x squared minus 1 L. Okay, so this comes out of nowhere, but for the sake of time, I will not show you. Even the Griffith textbook also, they skip the details of the solution. But you know, in the previous class, I was telling you guys that I taught engineering math 4, right? And we do solve this. In fact, we not just this. We show in engineering math 4, we derive the Legendre polynomials, and that class took the whole 2-hour lecture. In fact, it's 2-hour lecture and then cannot finish it in the next class. So it's not that it's very difficult. It's just power series solution, right? So it's just power series solution. So the process takes time to do it, and then it's a bit messy, but at the end of the day, this is the solution. But let's show some examples at least, right? So we are giving the formula. So let's see how to use the formula. It depends on L. So L must be integer. And let's start with L equals to 0. So L can be any integer. So L0 gives a solution, L1 gives another solution, L2 gives another solution. So let's say P0, right? So P0 means if we substitute 0, there's nothing here. Differentiate 0 times, that means you don't differentiate at all. This thing to the power 0, this becomes 1. So this whole thing becomes 1. If L equals to 1 means 1 over 2, right? And then this thing to the power 1, x squared, differentiate 1 time. So if you differentiate everything, everything will cancel and you get x. And then if L equals to 2, if you do this calculation again, you'll get half 3x squared minus 1. And then if L equals to 3, P3 is equals to half 5x cubed minus 3x. Okay, so some examples of the Legendre polynomials are in the lecture notes, so you can see it up here. Wait, where is it? Yeah, it's here, and the graphs are also shown here. So the first function P0 is a constant function, this horizontal line. P1 is just x And then P2 is 3x squared minus 1, so it's a quadratic function, and so on and so forth. Okay? Okay, any questions so far? So we are skipping the steps, doing a shortcut, so we'll just say given. The solution is given by this formula. Okay, but for our purposes, having the formula, we should at least know how to use it, right? So given this formula, can I get P5? What do? You put in 5, you differentiate 5 times, right? And so on and so forth. So in fact, because of all this formula, right, these results and the derivation give constraints to the possible values of M and L. Okay, so my PML, this thing over here, right? What we do know, at least we just keep in mind, the M here, the constraint is the magnitude is less or equal to 1, equal to L, which is to say that M mod is less than L. And this L itself must be a non-negative integer. That means it cannot take a negative number. Non-negative integers. Okay? So let us practice, right? So the Legendre polynomial itself is PL, but using this PL, we need to generate the PML. So how do we get the PML? So let's start with some examples. Let's start with P00 x, right? So P00 x is just 1, and then you put in differentiate 0 times, so everything is nothing, is just 1. How about P when L is equals to 1 but M equals to 0? So P1, so if you use the formula, right, this, no space. If you use this formula, this means that I need to do 1 minus x squared. The M is 0, so this is 0. And then I differentiate 0 times of P1. So what was P1? P1 was just x. Okay? And then let's do a bit of a more complicated example. How is P21 looks like? What does P21 looks like? So M is 1. So if I put in 1 over here, this means 1 minus x squared half. So this means there's a square root. M is 1 means I differentiate this 1 time. And then P2, right? So P2. So what is P2? Well, P2 is over here. P2 is, we found this over here, right? Or I do the full thing, 1 minus x squared half d dx. What was P2? Let's do the full thing. So you see at least once how it looks like. So P2 is 1 minus 2. I substitute 2 factorial, and then differentiate twice. X squared minus 1 square, right? So this is 4 times another 2. This is 1 over 8. This is x squared half. So I'm supposed to differentiate all this mess here. This is 1 over 8. And differentiate this twice. So differentiate 1 time, I get 2x squared minus 1 times 2x, right? So this 2 and this 2 will cancel with 4 of this, so I'm left with 2. And then I differentiate this again. So this is 1 minus x squared half d dx. So if I, this is basically x cubed minus x. So if I differentiate this, this becomes x cubed minus x. So it's 3x2 minus 1, right? And I differentiate one more time. I just get 1 minus x squared half, 1 over 4, I forgot, 1 over 2. So there's a 1 over 2. I differentiate this, this becomes 6x. So this cancel, this becomes a 3. So my final solution after I done this is I finally found P21. So P21 is 3x and the square root of 1 minus x squared, right? And remember my solution itself, right, is a function of theta. I need to change this back to theta. That means x is equals to cosine theta. So this is actually means 3 cos theta 1 minus sine square theta. So this is 3 cos square theta. Hang on, 3 cos theta. So this is 3 cos sine. Right? So yeah, it's a bit messy and a bit tedious, right? Even though we have the formula to create specific solutions, we need to jump through all these hoops. Yeah, it's a bit messy, right? So this is one instance where, unfortunately, quantum mechanics, well, a lot of physical problem is very complicated, right? Welcome to year 2 onwards. In year 1, we solve all the simple questions where all problems are described by 1 or 2 lines of equations. But in practice, right, this is just the hydrogen atom. You know, hydrogen atom is the simplest chemical element, right? Not to say not even rich helium or boron or molecules or diamonds or things like that. Then, yeah, so then that is even more worse. Theoretical mechanics. Okay, so you do know, you want to know how to solve, is it? It's basically the power series solution. Yeah, we will, when you will see this when we solve the R equation. The idea is kind of the same. But if you are interested, maybe I will attach the notes on how to solve this later. Yeah, after this class or something. So correct, yes. Yeah, remember when we solve the harmonic oscillator also, we use the power series, right? And then after that, we got the Hermite polynomials coming up. Over here, we do the same thing, and then we got Legendre polynomials coming up. Oh, so you got mentioned this also. Okay, yeah. Legendre is one of the common, so all these are called special functions. What we have learned are the Hermite polynomials. We have just learned the Legendre, and there's a few more, right? I don't know if I want to give the names, but those are important ones in physics, like Airy function, Bessel functions, and so on and so forth. There's many more. Gegenbauer, and other things. So yeah, let's see what we have so far. So our solution so far, well, we supposed to do separation of variables, right? We separated into RR, theta, phi, right? And we have solved these two already, right? So these two we have solved, especially the phi, right? So the phi, we got a constant times EIM phi, right? We have solved that already. And then this theta are the polynomials, which is PML cosine theta. So this part is the angular part of this equation. And this is what I meant when we call this the spherical harmonics. So usually in the textbooks and literature and in math also, not just in quantum mechanics, this equation appear quite often, and we call this Y. So theta phi. These are the spherical harmonics. Okay, so there's a constant A over here, and we need to determine the normalization condition, right? And again, I need to skip all the details, otherwise we don't have time to cover. But at least I will give you at least we have a taste or a flavor of spherical harmonics a little bit. And in the future, when you do, in fact, I think when you do electrodynamics, you need to use spherical harmonics again. But there's a constant A, so the constant A is determined by normalization. And wow, look at this messy, ugly function. And if I want to do the normalization, it's gonna be extremely messy, right? But which is why let's just skip it. I'll just give you the answer for pi. and then it is L minus absolute M factorial, and then L plus absolute M factorial, and the whole thing is square root, and there's an epsilon. Okay, so what is this epsilon now? So epsilon is negative 1 to the power m for m positive, and is 1 for m 0 or negative. Okay, so yeah, it is a huge mess, but in any case, we got the spherical harmonics is compiling everything just to see our answer and how it looks like is L minus m factorial, L plus m factorial, the whole thing square root. So this is my A, and then the exponential was found by solving the phi equation, and as I did not show you how to solve this, but I will attach the details later. It is this equation. Okay, so these are my equations of spherical harmonics. Okay, what time is it now? Attach, huh? Okay, yeah, I will attach. Oh, is it? Okay, that's good. That means you are thinking like a physicist, a theoretical physicist. Because the big contrast, right, among like, because we have taught like math students, science students, and engineering students. Usually engineering people, their job is something else, right? But they need to use some formula for certain things. So their job is, so usually when we teach math, people, they just want to memorize the equation or whatever, and then you plug it in, because they need to use it for engineering stuff, for other things. But for physics, we need to understand the theory. We need to open everything and understand where things come from, right? So that is a good way to approach a subject. So I will attach the notes, and it will even the notes, right? The notes that I do have typed up is only solving for the case of m equals to 0. And just plugging in m equals to 0, it becomes the equation for the Legendre polynomials only, not yet the associated. And that was the class that took more than 2 hours. But yeah, it's still essentially the power series method and all those things. But I guess for now, let's just keep this as our spherical harmonic solution. What we will go through the details is the radial equation. Okay. Yeah, I know what you mean. Yeah. Definitely, it's always interesting to read and study the lecture notes, right? But it's the exam part that makes everything stressful. So, yeah, I have the same situation most of the time. So now let's try to solve the radial equation. So the radial equation, let me write it down here. Okay, and it's equals to 2mr squared over h bar square, potential energy minus E, and then R, and it was equals to L plus 1 R, right? And another reminder that this V is a function of R only. Okay, so even solving this is gonna be a huge mess, as you'll see later. But first, let us, well, this is like a compact expression. So let me open this up. This is differentiating. This is a product rule. So differentiating this times this. So the first product rule is 2r dr, and then this part becomes second r square times, hang on a second, r square times the second derivative of r. Okay, and then this part is still the same, 2m r square h bar square v. This is some function of r minus E, r, and then this is LL plus R. Okay, so to solve this, right, this equation is a bit messy. So we need to first simplify this equation. We are going to change variables. So let us, instead of expressing in terms of r, I'm going to call this a new function u. U is just defined as r times big R, so that my du dr, it will make this function easy because du dr is, this becomes r plus r dr dr, and then the second derivative is dr dr, and then if I differentiate, I get dr dr, so it becomes 2. See? And then by the product rule, you need the second derivative of this as well. Okay? So I'm going to substitute this into this. See, this one looks almost similar to this. In fact, if I multiply both sides by r, it will be exactly equal to this part over here. So it's 2r dr dr plus r squared second derivative r. Okay, so we're going to substitute this into the radial equation. Okay, so this whole thing kind of shortens into du dr squared. So that makes things a little bit easier, right? And then this is just 1 over r times u. So let us put this in carefully. V minus e. So this becomes u over r. Okay, and then same thing on the other side. This becomes u over r. So this r can cancel with 1 r here, and then there's another r down here. Okay. Yeah. So let me bring the r downstairs, right? So if I bring the r downstairs, there's no more r here. And then bring the r downstairs. Now it has to become r squared. Okay. Then so what we're going to do is I will multiply both sides by negative h bar square. So now I bring up the h bar square over 2m. So this becomes plus this u, right? This plus vu minus eu, and then I multiply by negative h bar square over 2m, so it's a negative, and I bring this over, so it becomes a plus. So this becomes plus h bar square over 2m, ll plus 1, u over r square equals to 0. Okay, then this is just manipulating, so not doing anything special. So now I bring the e to this side. So if I bring the e to this side, what do I have? So I got h bar square over 2m du dr. Okay, and then v times u and all this thing times u. So I can just factorize the u out. So I got h bar square l plus 1, and then downstairs is 2m. This is 1 over r squared times u, and on the right hand side is eu. Okay. This is page 5 already. Wow. Page 6. So everyone follow so far? Let's see how's everyone doing. The same story going to happen tomorrow. I assume you guys are talking about theoretical mechanics, right? Yeah. Theoretical mechanics is deceptively difficult, because even among me and my classmates, we thought that, oh, theoretical is like classical mechanics, it's like Newtonian mechanics, it's like 400 years old. So we kind of like didn't take it seriously. And then quantum mechanics is the exciting one, is the newer modern physics topic. But both are kind of equally messy, right? Okay, so this is still, I still haven't specified what is the potential energy yet. Hang on, I forgot to check the time. Okay, so the potential, so let's talk about the hydrogen atom. Okay, so now I specify my hydrogen atom. My V is negative E squared over 4 pi epsilon R. Okay, so that means this is an inverse of R, this is inverse of R squared. So my equation now looks like this. okay, plus this is negative E square over 4 pi epsilon 1 over R, and then this is H bar square LL plus 1 over 2m. This is 1 over R square. This is U. This is EU. Okay, so now my equation, like, well, it's still, we are supposed to simplify, but it doesn't look that much better, right? We'll get there soon. But for now, let me do one more step. Let us divide the E downstairs. Okay, du dr square. And then if I divide the E down, it's going to become E square over 4 pi epsilon E. This is a coefficient of 1 over R, and H bar square LL plus 1, 2m E, and then 1 over R square U equals to U. Okay, so it looks like still very complicated, but actually this is also another thing we need to train and to learn in physics, is that even though it looks complicated, right, we need to see it's actually not as complicated. It's just messy because it contains a lot of constants, right? We need to recognize that there's a lot of constants everywhere. So if I just, because constant times constant divided by constant are still constants, so I can just, yeah, I will just call this by something else altogether. So I'm going to let kappa 1 over kappa square to be equals to this term, H bar square over 2me. Okay, remember, right, E is a negative energy, it's a bound state. Hydrogen atom, our energy levels are going to be negative. Okay, so I'm going to call this as kappa, so that my kappa itself is the square root of 2me over H bar. And then there's a, and also later I will need this 1 over E is going to be 2m over kappa square H bar square. Okay, so if I do this, then yeah, it's actually not that messy. It's just a bunch of constants everywhere. And then plus this thing, so plus 1 over E, there's a 1 over E here. So there's a negative E square over 4 pi epsilon. This is the electromagnetism term. 1 over E, I replace with 2m over H bar square kappa square, 1 over R, and then this is minus 1 over kappa E L plus 1. So this is basically H bar square over 2me minus, so this makes it into a minus kappa square, and then this is R square, and then this is U, and on the right hand side is still equals to U. So let me bring this for later. I will come to the left hand side, so this becomes negative U equals to 0. Okay, so does it make it simple? Yeah, we are going there. We are reaching there already. It is starting to become simpler, because minus minus, it becomes a plus. Okay, so this becomes 2me square, and then I got 4 pi epsilon H bar square, and then there's a kappa square. But notice, right, the kappa and R seems to stick together. So let me put one kappa here. There is one R. I will put kappa R over here. Then this becomes LL plus 1. And then this is kappa R square. This is U minus U equals to 0. So actually, I should have factorized the U outside. So yeah, we shall do that. So we will change another variables because, like I said, right, the kappa and R seem to stick together. So let's just call this whole thing rho. Okay. Call this entire thing rho, and then this thing, this cancel becomes 2. So this thing is a bunch of messy stuff, but these are all constants. So let's just call this rho 0, right? So rho 0 is just me square over 2 pi epsilon H bar square kappa. So finally, this becomes a bit better now. This is just second derivative of U with respect to rho square. Right, and then this is rho 0 over rho. This is LL plus 1 over rho square, and then minus u, so it just becomes minus 1 u equals to 0. Okay, so finally we have we spent all this time just simplifying the equation. We haven't even started solving it, but at least it looks a bit better now, right? It doesn't look as scary as before. L plus 1 rho square u. Okay, so we are now solving u as a function of rho. Once we have found the solution, we just replace this in terms of r, and then the kappa later we will replace this in terms of this. Okay, so yeah, like 50% of the problem is actually simplifying it, but once we simplify the problem, then solving it may not be as terrible as it initially seems. So this is the equation that we want to solve now. Okay, does anyone have any questions? Yeah, it's been a while since he didn't come. I guess so lah, right? It's a semester. As the semester goes on, people become more and more busy and blah blah blah. I think this is a common, yeah, even myself and my classmates, we all think that, and then we run into trouble. But hopefully, like, we kind of arrange it in a way that is hard, but you know, we are practicing and we are using, like, seems we are doing the power series solution all the time. So the it's hard. We learn advanced techniques, but the techniques we were using are consistent. So it is like, it will make us easier for us to understand and things like that. Okay. See, what we're going to do next is something we did before. What do we mean last time is to, how do we solve this equation? We can't, the first thing is we can't get the solution, so at least we check the asymptotic behavior, right? That's what we did last time. This whole solution is still a bit complicated, but if rho is large, then for large rho, the equation simplifies, so we can get a shape of a solution when rho is large. And then here we will also check when rho is close to 0. And then we see what does the solution looks like when it's close to 0. And then we join the solution in the middle by finding the f. And then we do the power series solution. Okay, so we are check. The first thing that we do is we need to check the asymptotic behavior. Okay, firstly, let's look at what happens for large rho. So when rho is large, right, that means I'm like kind of far away from the hydrogen atom. What happens to the wave function? Well, when rho is large, these two terms becomes small, so it becomes negligible. So my differential equation, this is rho, sorry, this is rho. My differential equation is, for large rho, is only contains the u on the right hand side. The other two terms close to 0. Okay, so the solution to this is, yeah, it's just u. That means it's a constant e negative rho plus this is asymptotic be positive rho, right? So this was my solution, but I don't want this solution because this is an exponential where the u keeps getting larger and larger, which it will make it not normalizable, right? So this term will become infinity as rho goes large. So we are going to set b equals to 0. So in other words, we have concluded that whatever this is, we can't really find the solution yet, but at least we know that when rho is large, the function looks like this. Okay, so that's what happens when rho is large. But what happens when rho is small? So when rho is small, close to 0, so when rho is close to 0, then this term becomes large, right? So it becomes way larger than the number 1. In fact, this square term will be even larger than this. So this part is the dominating term. So my solution now becomes asymptotically LL plus 1 rho square u for large rho. Okay, And this is a differential equation approximately. We can also get the solution for this. The two solutions that you can get is C rho L plus 1 plus another constant rho negative L. Okay, so you can check if we differentiate 2 times, this is going to be equal to the left hand side. Okay, so now, well, this we are talking about small rho. So this one is 1 over rho to the power L. This term will diverge as rho becomes small. So we are going to set d equals to 0, right? So therefore, we have concluded that for rho small, it is something like a constant times rho L plus 1 when rho is small. Okay? So when rho is small is this, when rho is large is this. So that means we can kind of like estimate, or not estimate, but we kind of get a rough idea of what does the function looks like for these two distances. So for small distances, it is like L plus 1, right? And for large distances, it becomes e to the negative rho. So generally, we can guess our solution looks like this. Okay, so you can check, right? So when rho is small, this term becomes negligible and this term becomes dominating. So this is approximately like some stuff times, well, let's go to large rho first. When rho large, right? So when rho is large, this thing will become dominating, right? And then this term becomes dominating when the rho is small. Rho L plus 1 when rho small. Okay, so that means this something here is what we need to determine next. So this is, we don't know, so let's just call this a function of rho. Okay, so this function of rho is kind of looks like this. So that means we can estimate or guess our solution. Our ansatz is something like this. Okay, so how do we get f? Well, the only thing we have left to do now is to substitute this into our differential equation and see what we get. Okay, and then that new differential equation is what we will solve by power series. So I guess we should take a 10 minutes break and we continue solving after this. Okay. Yeah, it's kind of like, it's like a presentation kind of thing, right? So the ugliness that you people hear as in the public, like the videos and articles and things, we don't see the ugly part, but you know, the real physicists doing the job, they will need to deal with all the ugly and messy stuff. Yeah, so how about, yeah, so that is what we want to do next time. So if rho is not very large and very small, then this something will play a role. Okay, so that is what we will, this is what we will do next. Okay, so let's, if no one here is Spider-Man, then you can't use this excuse to miss the deadline. Okay, full screen. Am I recording? Test. 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 Okay. Recording. Wait, what happened here? Wow, so fast. Yeah, this this one we're not doing this. This is scattering. So because it looks like a solid angle equation. Recording here, yes, okay. Okay, so wait, full screen, full screen. We want to now, our function has been kind of like, you know, estimated until it looks like this form. So now the next thing to do is, well, we need to plug this into our Schrodinger equation and try to get the solution from there by the power series method. So our Schrodinger equation, not, well, our separated Schrodinger equation is now this, right? Am I recording? Yeah, yeah. It's now this. So it needs a second derivative. And again, I think I will skip most of the steps here because it's very boring and very tedious. But the first derivative, this is a multiplication of three functions. So if you try to differentiate this, you need to use the product rule. And after you simplify, you're going to get something like this. So plus 1 minus rho f plus rho df d rho. Okay, but this is only the first derivative. You need to, second derivative, you need to differentiate this one more time. Okay, so differentiating one more time, you will get a huge mess, but you can collect the coefficients and simplify. So I will just give you the results here. Okay, L plus 1 over rho minus 2L plus 1 plus rho, and then F. And then this one is 2L minus 2 rho plus 2 df d rho, and then plus rho d2f d rho square. Okay. Yeah, so I think you know what I'm doing, right? I skip a few steps, but this just means that if I differentiate this 2 times, I get a bunch of stuff that I need to simplify. Okay, so this one is just using your calculus 1 knowledge, but again, right, in year 1, calculus 1, your product rule examples and exam questions are the easy ones, but when we want to solve a real problem, it gets messy really fast. Okay, so now we substitute this into the ODE. So on the left hand side is basically just the second derivative, so the whole of left hand side is just this whole chunk here. So rho L e to the minus rho L plus 1 over rho square minus 2L plus 1 plus rho F, and then all this has a 2, so let me put the 2 outside. L minus rho plus 1 df d rho, and then this is rho d2f d rho square, and what's on the right hand side, so there's no space already here. On the right hand side is this, and then u, so just put a u there. So it's just 1 minus rho over rho plus L plus 1 over rho square, and then rho L plus 1 e to the negative rho, and then F. Okay, so well, this thing we can almost cancel, but there's a rho L plus 1, there's a rho L, so the rho, there's one rho here, I will put it inside, so it will become rho minus rho 0, and then L plus 1 over rho, right? And then this is rho L E F. Okay, so now these two can cancel on both sides of the equations, and then this contains F and this contains F, so I can simplify. In fact, now that I cancel, right, this is, now we can compare the hang on a second, this is rho power 1, that's why we did it, right? So now we compare, both sides are now the same, so these two can cancel also, and then this part will cancel with this part, right? This is exactly the same, and then this part I carry over to the other side. Then I just left with positive rho 0 minus 2L plus 1 times F, and then this is 2L minus rho plus 1 df d rho, and then rho d2f d rho squared equals to 0. Okay, so this one next step is nothing interesting. It's just my habit that I must see the highest derivative on the front. Okay, it's just your personal taste. And then plus rho minus 2L plus 1 F equals to 0. Okay, so so at the moment our equation now looks like this. This is a second order ordinary differential equation, and we are going to use the power series method on this. Okay, so let's do that, the power series method. So power series method again. We are going to let F be a series. So J starting from 0 generally to infinity, but we will also give a reasoning that this must be finite, rho to the power j. Okay, so if I assume my function takes this form, let's see what happens if I substitute this. So I'm going to need the first and second derivative. So my df d rho is doing the same as before, right? Differentiate this one time, I got cj, the j comes down, rho j minus 1. So if I differentiate this another time, j from 0 to infinity, cj, j, and then j minus 1 comes down as well. This becomes j minus 2. Okay, so if I plug this into my ODE now, then this becomes what? So the first term is my second derivative, so rho times j 0 to infinity and all this stuff. So just copy paste everything first. I will manipulate and simplify this later, right? J minus 2, and then this is 2 L plus 1 minus rho. First derivative is all this, cj, j, rho j minus 1, and then this is also, all these are constants, and then just f, so f is just cj rho j, and this whole thing is equals to 0. Okay, so let's try to simplify this equation a little bit as much as we can. So the first thing that we can notice is I will multiply the row inside. So if I multiply the row inside, this will become j minus 1. Okay, so this j from 0 to infinity, cj, j, j minus 1, and then this is also rho j minus 1. Okay, and then this is another, so this part is a constant times the series of j minus 1. This part has a row which I can multiply inside. So I'm going to split this into two terms. Okay, so the first part is just the summation from infinity of 2l plus 1 cjj rho j minus 1, and then plus the second term is the negative 2 rho goes inside, so I got negative 2 cjj rho, the rho multiply this becomes a j, and this constant goes inside is still a constant, so I got rho minus 2 l plus 1 cj rho j. Am I sharing screen? Why do I feel like I forgot something? I'm recording. Yeah. Okay. Why do I feel like I forgot to do something? Everything okay, huh? Okay. I don't know why. I seem to be, I forget to do something. In any case, so these two terms is j minus 1, this is rho j, so this one can group together, these two can group together. So this is a series of j from 0 to infinity. And then we can tidy up by recognizing some common factors. So both terms have cj and rho, and j minus 1. So it's j minus 1 plus this. Okay, so I can pull everything out. This is pull everything out, this becomes j. So the first term just have j inside, the rest I will factorize out. And then this is plus 2l, no, this is j minus 1, right, j minus 1, and then this is plus 2l plus 2, and then the cjj can be factorized because it's common to both. Okay, then this part, now what does this look like? So this part is just rho 0, 2l minus 2, and then this is minus, so the common factor is cj rho j, so cj rho j, so this is negative 2j, so 2l minus 2j, cj rho j factorized out. Okay, then this one can simplify, negative 1 and 2 just left with plus 1, so this is j, and then I got j plus 2l, 2 minus 1 is 1, and then this is cjj rho j minus 1. Now how about this? I think that's it, right? That's all. We can't do much here. So this just, we can factorize a 2, at least that much. J plus 1 plus L. Am I right? Cj rho j equals to 0. Okay. So now we do the same trick that we did last time. This is a power of j minus 1, but this is j. So my series, I can shift this to make it the same power. To make everything the same power, I will let k equals to j minus 1. So in other words, I will substitute above to be k plus 1, right? And we can make it the same because the first term, right, the j0 term, so the j0 term means k equals to negative 1 is 0. So the sum starts from k equals to 0. Or in other words, j equals to 1, right? So that means I can substitute k. If I substitute k is j minus 1, right? If I follow this, then I need to start my summation from negative 1. But negative 1 is already 0, no need to write. So you just start from k0. And then this is, j is k plus 1. So k plus 1 plus 1, this becomes k plus 2. So this is k plus 2 plus 2l. So this is ck plus 1. J becomes k plus 1. Rho to the power k. Do you agree? OBS. Yeah, OBS is recording, right? I'm recording. Hang on, let me just check. Yep, it's running, I think. It's saving. So I don't know, maybe my brain just playing tricks with me. But for this case, this one nothing special. I'll just call this k so that everyone is having the same constant. So this summation is just replacing everything by k plus 1 plus L ck rho k. Okay, so that now everything is a summation with k from 0 to infinity. This part is k plus 2 plus 2L ck plus 1. This is k plus 1 rho k. And then this is another summation, but it's also k rho 0 minus 2 k plus 1 plus L ck rho k equals to 0. So now everybody has rho to the power k, so I can factorize everyone to have the same, just put everyone in the same equation, and the rho k, pull it out, so I got k plus 2 plus 2L k plus 1, and then this is plus rho minus 2 of this plus 1 plus L. So this is ck plus 1. This is ck, and then this is rho to the power k equals to 0. Okay, so now we have kind of like having everything in terms of this k, and I want this summation to be 0. So again, remember that we kind of use the same reasoning as last time. How do I make sure this equation is satisfied? Well, one way to satisfy this equation is to make everyone here always 0. Then it's definitely the right hand side will be satisfied. So this equation is satisfied if this whole thing here is 0. If each coefficient of rho k is 0, which is to say that this term is 0. So this is k plus 2L plus 2, k plus 1, ck plus 1, plus this stuff is equal to 0. So now we got the recursion relation for the coefficients, right? So this is 2 k plus 1 plus L minus rho 0, and this is dividing by this thing here, so it's k plus 2L plus 2 k plus 1 ck. So we got the recursion relation, and let me just change for personal taste. Let's change this back to j, so that my recursion relation is now a function of the index is j. 2 j plus 1 plus L minus rho j plus 2L plus 2 j plus 1 Cj. Okay, so now we got the recursion relation for this power series. So you see one main difference from harmonic oscillator. Harmonic oscillator is plus 1. Harmonic oscillator is j plus 2, right? So for the harmonic oscillator, they skip by 2 steps. But for this one, it's skip by 1 step only. Okay, so that is at least one. In that sense, it makes it slightly easier compared to the earlier case that we did. And how can we like narrow down our solution? So again, we do the same reasoning as before. What happens for large j? For large j, right, what happens? For large j, Cj plus 1 is, when j is large, right, so these two terms are dominating, so we find that this is 2j over j square times the Cj. So by the same argument that I did last time, so I guess I don't want to repeat it, Cj is approximately 1 over j over 2 factorial, right? And I remember Theory asked, what happens if j is an odd number? It doesn't really matter because this is just approximately a formula for large j, right? And we don't really need to know what is the exact number of this, because I want to say that we want to argue that large j doesn't happen. The j doesn't sum to infinity, because if it sums to infinity, if this sums to infinity, my function becomes, this is a coefficient for the exponential function, then not normalizable, right? So if sum to infinity, okay, so it's not normalizable, but therefore again the same argument that we did last time. So if I want to avoid this, that means the summation stops somewhere, stop at some finite term, because it's sum to infinity, this becomes like an exponential function. So to avoid this, we say that the series, maybe it stops at some finite term, finite, some last number j max, right? So some finite term. So that means my f of rho, the summation starts from j0, right? So it's 0 plus c1 rho power 1, c2 rho power 2. Okay, I don't need to go all the way to infinity. I want to stop somewhere. So let's stop at some number j max. So I stop here. So that means everything after this becomes 0. So how do we make this become 0, right? So if I want this to stop here, this means that my Cj max is, this is my last non-zero term. And since this is my last term already, the j max plus 1 must be 0. And according to the formula, how to get j max plus 1? Well, this is the recursion. So this is 2 j max plus 1 plus L minus rho 0. And then this is j max plus 2L plus 2 j max plus 1. And then this is Cj max, right? So this is definitely not 0 because this is my last non-zero term. So in order to make sure this is 0, I need to this term must be 0. In other words, to make it 0, then this term must be equal to 0. So rho 0 must be equal to 2 j max plus 1 plus L. Okay? See, same reasoning as before, right? So hopefully it gets easier the second time you're seeing the power series method. The first time I showing this to you was everyone's brain was melting and things like that, right? But now that we have kind of we have seen this before, so the second time seeing it is hopefully not that scary. Now let's look at this term. J is the power, so J is some integer. L was the L that we got earlier. We have, because it's a Legendre polynomial, the L must be a non-negative integer. So integer plus integer plus integer, everyone here in total is still another integer. So let's call this n. Okay. In other words, we define n to be equal to j max plus L plus 1. So we notice that n minus L plus 1 is equal to j max, and j max is the last term. So j max could be any number from 0 to some positive number. So this is a positive number. And now we got the relation that the n value must be greater than L plus 1, or L must be less than or equal to n minus 1. I hope you're getting flashback for this, because this is probably something that you have learned in the modern physics, right? These are the hydrogen quantum numbers. The L quantum number must be less than n minus 1. Okay. Second time body melt. Okay. So the exam question is, yeah, it could be. I mean, the exam question will be things like asking you to, to calculate this kind of things. So basically, like for higher level courses like theoretical mechanics and quantum mechanics is to understand the theory first, right? So that is also another main departure from your high school things. Like in year 1 and high school, students always like to memorize formula, then they just plug in the formula, get the answer, right? But over here, we are going deeper now, is to understand where the formula comes from. And plugging in formula is no longer the emphasis of what we are doing. Okay, so how much time do we have left? Okay, I think we got time. So, yeah, so you said brain annihilation. Then you should apply the creation operator to the brain. Then it doesn't happen, right? So now what we want to do is to, we can get the energy level. So as I said, this n, I claim that it was the hydrogen n quantum number. So let's see exactly how it works. Okay, so in other words, this whole thing, we'll just call this n. And 2n is equals to rho 0. Now, what was rho 0? Remember, rho 0 is a bunch of constants which we define so that we don't need to write so many constants all the time, right? So where was it? Where was rho 0? Okay, so long ago. Rho 0 is here. Okay, so we define rho 0 is all this bunch of constants here. So let's put it back. So let's put this back. The rho 0 is me square over 2 pi epsilon h bar square kappa. This is equals to 2n. Okay. Now this 2n, let me bring this down. So this becomes 4 pi epsilon h bar square. Kappa is equals to n, and then there's the kappa, right? So kappa was also something else which we defined over here. So let me just put kappa up here, right? So that this is me square over 4 pi epsilon h bar square, and then the n I bring down, right? So it's 1 over n. So what was kappa? Kappa is the square root of a bunch of stuff. So if I square kappa, right? Kappa square is going to be, well, let's square this first. So kappa square is equal to m2e4, and then this is 16 pi square epsilon square h bar square 1 over n square. And remember, what was kappa square? Kappa square is actually just negative 2me over h bar square. So we can, well, this one square, this becomes power 4, but h bar square will cancel, it will come back to 2. And then this part has 1m, it will cancel with this. And then if I bring the 2 down, this becomes 32. So I'm left with E. The negative also, I bring this over. So this becomes ME4 over 32 pi square epsilon square h bar square 1 over n square. Right? So you see something familiar? This was our hydrogen energy level, right? So this was our energy level using the Bohr model. So if you calculate this, this is the mass of the electron, right? Because we are talking about the motion of an electron around the hydrogen atom. This is the charge, and then this is permittivity square, h bar square. So if you calculate all the values, you get 13.6 eV, right? So this is a number that most physicists always remember, because this is the ground state energy of the hydrogen atom. So using the power series method, we have re-derived the energy level of the hydrogen atom. That's pretty amazing, right? In modern physics, you have learned how to solve this using the Bohr model. So this was the Bohr energy levels. But we have re-derived this. So previously, when you're using the Bohr model, that was like the old quantum mechanics, right? We are still treating the electron like a point particle, no wave function anywhere. But the way to derive this is to make some assumption that angular momentum must be quantized. So that was the assumption that the Bohr model was making. And by this assumption, we can calculate the energy. After a few steps, you got this formula, right? If you remember last time, that was what you guys did. But now it's like Bohr model is not 100% accurate, right? But even though it's not 100% accurate, people did the experiment to measure the energy. It seems to be correct. So, but now a few years after that, people developed the wave function theories, you know, the psi, the Schrodinger equation, and well, we need to check whether the Bohr model energy levels are correct. So we have just done that, right? After all this calculation, separation of variables, doing a power series, we have found that, yeah, we have re-derived the equation again. So at least we kind of know that we are on the right track. So then, yeah. How many paper? So far, I'm at page 9. So 9 pages. So what is M? So we'll come to M later. Yeah, M is the quantum number in the angular, the spherical harmonics. Actually, right, 1 plus 1 is not easy to prove. Right? That's the logic. The proof of 1 plus 1 equals 2 using set theory is actually pretty long. It will take a few pages also. So yes, you're asking M. We'll come back to M later, but let's focus on, at least go to L first, right? So we have found our solution, our power series solution. Yeah, how many pages? We're at page 9. Our power series, it is a series where the coefficient is using this recursion relation, right? So this recursion relation, it contains L and J and rho 0, and it will determine the J maximum. So that means my power series will determine the N and L. So in other words, to actually write down our function, right, we need to look at a choice of, let's choose a value of L and N. But we cannot choose any two numbers, because the only way we got this solution is these are integers, and the only way these are integers is L must be smaller than N minus 1. So that satisfies L less than N minus 1. Okay, so let's see what are the possible choices of NL. So for every choice of NL, we can determine the J max using the formula, right? And once you got the J max, we can finally get the F. Okay, so the ground state solution of the hydrogen atom, the ground state solution is N equals to 1, right? So N cannot be 0, otherwise it's infinity. So N is 1, 2, 3, dot, dot, dot. So the ground state solution is 1, and the only possible L is 0, right? Anything it cannot satisfy already. So if n is 1 and L is 0, the J max is the J max is 0, right? So L is 1, n is 1, 0, 1, then J max is 0. J max is 0, that means this is a series of one term. Okay. So if I choose n equals to 2, but let's say L is still 0, right? So if you calculate the J max increase by 1, so this is 1, that means the J maximum stops at 1. Okay. So if you look at some other examples, let's say 3, 0. So if you put 3, 0, then your J max is 2, and then this is C0 plus C1 row plus C2 row squared. Okay, and then if you try L equals to 1 here, the J max becomes 1, so it's C0 plus C1 row. And then you can keep on doing for all the other choices as long as you satisfy your function over here. Right? So the solution is R. It depends on n, and whatever this n and L is, it is a function of R, but we have found that it is equals to e to the power negative rho, and then rho to the power L plus 1, and then the function rho. Right? So this function, which we found to be C0 plus C1 rho, whatever this is, right, you stop at the J maximum. Okay, but remember this is the function of R, so we need to put back in terms of our original variables. So let's do that. Restoring original variables. Okay, so how to change rho back to R? Remember we define rho as kappa R. So to change back to R, we take rho and divide by kappa. What was kappa? Kappa is the square root 2me over h bar. So this is h bar over square root 2me rho. This contains the e over here, right? So yeah, just now we simplify the equation, but we need to extract back our quantities. We need to put back the mass. So square root of 2m, let me keep it aside. Negative e was the formula which we found earlier. Negative e was all this stuff, but it's 1 over e. So I flip this. So this is square root of 32 pi square epsilon square h bar square over me4, and then the square root, and then times the rho. So h bar square square root, with this it will give me a h bar square again, and then 2, so square root, so let me put this in, right? So if I put this in, then I got 2 and 2 cancel, it becomes 16 pi square epsilon square, h bar already taken out, and then this becomes m2e4, the square root of rho. So this is just h bar. Actually all these are perfect square. This becomes 4 pi epsilon over me square times rho. So this is R. Wait, where's my n? My energy level depends on n, right? So 1 over n square. So that means I forgot the n square here. N square. So this is n. Okay. So now again we recover something familiar. Let me rearrange this a little bit. This is 4 pi epsilon. This is h bar square. This is me square. This is n times rho. So this is actually what you learned in the Bohr model as your A0, the Bohr radius. So we found R is just the Bohr radius times your quantum number n times rho. So to change everything back to R, you just take R divided by Bohr radius n. Okay, so A0, the Bohr radius, is just a shorthand for this. And see, for n equals to 1, you get 1 times the Bohr radius. So this one, you can kind of see how this relates to the Bohr model by this R. I mean, the scale of this. But remember, now we are talking about wave function, right? So this is not, the R itself is not exactly the position of the electron, but the wave function of my electron is a function of R. right? And we use the wave function to get the probability distribution and everything. So yeah, this is page 10. So we are at page 11 now. Yeah, it's a very troublesome, right? Even I feel tired going through all this. Okay, it feels like I've been exercising. Like, wow, getting the hydrogen wave function is very messy. Yeah, right. So exactly, is we skipped the Legendre polynomial to reach it, and it already took our entire class. So the last thing to do is, yeah, let's put back our function. So the radial function. So we got r already. So my radial function NLR, right? Actually, in fact, I made a mistake. This is not, we are not finding r. This is just u, right? Our equation was for u, the function u. You know what I'm talking about. I'm lazy to flip too many pages already. We need to put back our r. So it is, how do we define u? So u is r times big R. So to get back our capital R, we need to divide by r. Okay. Now this u was what we have found to be rho to the power of L plus 1 e to the negative rho, and then this is my function rho. So this was the series that we have found using, and then the coefficients, we got the formula for recursion relation, all those things already, right? So this is already r, but this is rho, so we need to restore r again. So we need to substitute rho equals to r over a naught n. So this is 1 over r, this is r over a naught n to the power of L plus 1. Then this is e to the power of negative r a naught n. And then whatever this function is, all the rho I replace with a naught n. Okay. So yeah, I have found my radial wave function. My radial wave function is, I can simplify slightly here, but doesn't really do much, right? It depends on what is the L. And then this is r over a 0 n. And then this f is a polynomial, right? And I have shown you how to get the polynomial. This f is the summation from j to j max, which is n minus L plus 1, right? And my coefficient is Cj and times rho j, but I need to change everything back to r, right? And to get my Cj, it is 2j plus L plus 1 minus rho 0. This is j plus 2L plus 1. This is j plus 1, Cj. Okay. So yeah, we have found the solution for r already. So we can finally assemble our final wave function. So notice that it depends on 3 quantum numbers, right? Our solution depends on what is the n, what is the L, and what is the m. And this L must be less than equal to n minus 1. And whatever this m is, the absolute value must be less than equals to L, right? So this is the constraint of the quantum numbers, because other numbers will not satisfy the equation. And then my wave function will, since it depends on these numbers, we label them by NLM. So for different integers that I put in here, we will get different specific functions. But generally, for whatever this is, right, we have found this to be our radial wave function NL. The way to construct the NL is given by all this stuff here. And then the angular part is given by the spherical harmonics. Okay, so the radial function, to show you a picture of this is, shall I show the textbook? It's here. So this is the plot of the first few functions of R, and then this table shows you a few choices of R. So the lowest, the ground state is 1, 0. So 1, 0 is the function R is given by this. And then 2, 0 is given by this. So the higher, the more excited the state, the function becomes worse and worse, right? So it becomes more and more complicated. And the way to construct this is using the method that I showed you just now, right? And then for the angular wave functions, you can see them here. Yiming has already plotted the graph last week, right? Yeah, so you know how to plot this. So this is from the textbook, right? So the 2, 0, 0 state, right? The third excited state, L equals to 1, and then M equals to 0, right? So the M quantum number is for the phi direction. So for this case, they plot all the M equals to 0, but for the M equals to 0, you notice that it's actually the complex phase, so it doesn't really affect the shape of the probability distribution, right? So that's why people don't really plot this. So the probability distribution for the angular parts, they look like this. So for the ground state, right, the state is spherically symmetric. That means for a hydrogen atom at the ground state, there's equal chance of finding the particle in any of the angles, right? Could be up, down, left, right. It only depends on the R. So the further away you are for the R, the distance, then where's the R function? The probability becomes lower, right? So the R1 is here, this one, right? So the further away you are, the faster it goes to 0. Then for the next excited state, you get different possible shapes. That means for this type of shape, right, this is the P wave function in chemistry. So that means you have a higher chance in finding up here and down here, but on the equator, the probability is low, right? And then you can, for all the other cases, you construct accordingly. Okay, so yeah, I think that's about time for today's class. And also, I feel exhausted just doing this power series solution. Does anyone have any question? Yeah. Yeah, you forgot what rho is. Yeah, right? So, yeah, remember the rho is R over A0N. So that is like a lot of this is like a long-term calculation. You spend quite a lot of time trying to solve an equation because the differential equation is difficult. Okay, so if there's no other question, I think that's all for today. If anyone wants to present on Monday, let me know. We continue presentation again on Monday. And next Monday, we will do a more is unavoidable, right? We'll go back to bra-ket stuff momentarily, and it will not be as exhausting as this, I hope. So yeah, so let's see what we'll go to angular momentum basically. Next Monday we study the theory of angular momentum. So let's stop the recording.